Hello and welcome back to this third example of nodal analysis. And again, if you haven't seen our previous video, the introduction to nodal analysis, it's well worth watching that first. We're going to dive straight in and we're not going to cover things that we've covered previously. As well as that, we've also done two previous examples which are worth watching first. They're simpler circuits. This is a bit more of a complicated example. So let's get started, and we have in this circuit another example of something that might prove a little bit confusing at first when we start to look at these nodes that we've marked on the circuit. We have three unknown nodes here. We've called them 1, 2 and 3. And we have our reference node here, which we've marked as 0. So let's just look at this node 2 for a second, because what's often a bad habit is people look at these sort of junctions in the circuit and mark these as nodes 1, 2, 3 and 4, for example. But it's important to note here that if we've got 2 points that are connected by a short, they're the same node really. They're going to have the same potential, the same voltage, and so we can't give them separate nodes or numbers. We're classing these as one node, as it were, and that's node 2 in this case. So don't get caught out making things much more complicated than they need to be by marking on more nodes on your circuit than you actually have. Here we've got 3 unknowns, just like example 1 and the introduction video that we've seen previously. The same actually applies here at the bottom. We have this, this junction here. That's again just a case of being directly connected by a short to node 0, and so this is still our 0 node, our reference node at this point here as well. So at first glance this circuit looks a bit more complicated than our previous examples, but it's not. It's another instance of 3 unknowns, and again we're going to handle this in a similar manner to the way that we set up our system of equations in our first introduction video. Again, if you've not watched that video, it's well worth reviewing that first, because I'm going to derive a system of equations very quickly here, but not go into too much detail as we've done previously. So here at node 1, we have a current leaving this node, this 3 milliamps, and so we have minus 3 times 10 to the minus 3 amps, and that's set as equal to V1 over 3k in parallel with 5k, because we have our voltage V1, we have 2 resistances in this case directly connected to that node. We have our 5k resistor here and we have our 3k resistor here, and they're in parallel using this is my shorthand notation for parallel resistors here. Subtracted from that, we don't have a resistive path that takes us directly to node 2. We're only interested in resistive paths in this case in the form of V over R. Now here we have a connection directly from node 1 to node 2 via this current source here, but we've already taken the current into account in the left hand side of the equation, and so we're going to say minus 0 V2. There's no sort of resistive connection from node 1 taking us to node 2. And then we're also going to subtract, again in the form of V over R, we're subtracting anything that takes us directly from node 1 to node 3, the voltage V3 here. And again, we can achieve that via this 5k resistor. So again, we're subtracting minus V3 over 5k. Our second equation for node 2 here. So remember, node 2 encompasses this sort of short, this stretch all the way from here to here. And do we have any currents directly entering or leaving this node here? Well, yes, we've got this 1 milliamp. It's leaving the node, and so it's a minus as we express it in this system of equations. So we have minus 1 milliamp leaving the node. We also have this 3 milliamps that we've mentioned before, and it's entering this node. It was leaving node 1, it's entering node 2, and so we have a positive 3 milliamps entering. So we have two current sources here. We have one leaving, one entering. So positive 3 milliamps and negative 1 milliamp. So I'll just express that here as 3 minus 1, and that's times 10 to the minus 3 because it's in milliamps. On the right hand side, let's start with the V1 term. Are there any resistive paths that take us directly from node 2 to node 1? No, again, we've discussed this current source before, but there's no resistive path, so that's minus 0 V1. To the node in question, we're at node 2 here. Any resistances directly connected to that node there? Well, yes, we have 2K here connected to node 2, and we have 4K connected to node 2, and so we have plus V2, because we're at node 2 for this equation, so plus V2 is the node in question, and the voltage in question, divided by 4K in parallel with 2K. And V3 all the way over here, do we have anything taking us from node 2 to node 3? Yes, we can go via this 4K resistor, and so we're subtracting finally V3 over 4K. Last equation for our third node, so we're at node 3 now. Do we have any currents connected directly to node 3 of our circuit? Well, the answer is no, and so we have 0 on the left-hand side of our third equation. Is there anything that takes us from node 3 all the way to node 1? Yes, we can go via this 5K resistor, and so again it's subtractive, we're going to another node, so we're subtracting V1 over 5K. Is there anything that takes us from node 3 to node 2? Yes, we can go via this 4K resistor, so we're subtracting V2 over 4K. And finally, node 3, well, we're at node 3 for this equation. Are there any resistances directly touching this node? And we have 3. We have 5K, 4K, and 1K, all in parallel from the sort of point of view of this node here. And so we have V3 over 4K, 1K, and 5K, all in parallel there. Like we've done in our previous examples, let's handle these parallel resistances first. I've used this shorthand, this double slash sort of notation for two resistors in parallel. Let's actually work these out. At one point we have 3K in parallel with 5K, or 3,000 in parallel with 5,000. And that comes out as 1,875. And we have 2,000 in parallel with 4,000. That comes out as 4,000 over 3. We're keeping that as a rational number in fractional form. I'm not going to round that to a decimal. We have 4,000 in parallel with 1,000 in parallel with 5,000. That comes out as 20,000 over 29. Let's pop those back into our equation now, and we'll have something that looks like this. So rather than my shorthand notation, we now have some values there. And what we can then do is use this identity for complex fractions. We have a fraction which has a fraction as its denominator, and we've mentioned this in previous videos, but if we have something in the form of this, A over B over C, then that's the same as CA over B. And so let's apply that logic here and rewrite our equations like so. And so we've got something that's a bit tidier now. Let's multiply all of our equations by 1,000 to begin with. This might not necessarily be helpful in other examples, but here down the left hand side I've all my currents are 10 to the minus 3 in milliamps. So multiplying everything by 1,000 is going to look something like this. Now what we can hopefully see at this point is we can simplify everything a little bit more, because what we can do here, equation 2, we could multiply everything by 4. That's going to get rid of all of these sort of 4s as our denominators here. It's going to simplify our equation a bit. Here on the right hand side of equation 3, I could multiply everything by 20. 5 goes into 20, 4 goes into 20, and 20 goes into 20. And so if we multiply everything on the right hand side here by 20, multiplying the left-hand side doesn't really matter because it's 0. We can simplify this equation a little bit. And finally, what to do with this first equation. The second and third equations were easy enough. We can multiply everything in equation 2 by 4. We can multiply everything in our third equation by 20. But here we've got this decimal in the first equation, 1.875. What can we do or what can we multiply by to get sort of nice whole number coefficients in this case? Well, let's cheat a little bit. We did this in our last video as well, but if you've got a decent scientific calculator that gives answers in rational numbers in fractional form when possible, then if you take V1 over 1.875, let's take that to the side here, V1 over 1.875. We could write that, if we wanted to, as 1 over 1.875 times V1. They're the same thing. Now, if you type in a calculator 1 over or 1 divided by 1.875, if you have a calculator that does this, it'll give you that result in fractional form as a rational number, and it'll be something that looks like this, 8 over 15. And that's to say that 1.875 goes into 15 8 times, as it were. And if your calculator doesn't do this, by the way, there's some conversion tools available. If you just sort of Google search a rational number calculator or something like that. But it just helps to simplify this a little bit in our case, because what we can do now, if we put that back into our equation, we have now 8 over 15 V1 or 8 V1 over 15. We can see now that we could multiply everything in our first equation by 15, and 5 goes into 15, 15 goes into 15, and so we're going to get nice whole number coefficients in our first equation as well. So just to recap, we're going to multiply everything in this first equation by 15. We're going to multiply everything in this equation by 4, and we're going to multiply everything in this equation by 20. And when we do that, we get these equations here. And hopefully you'll agree these look a lot tidier than what we've seen previously. Now, at this stage, we can use matrix methods. We can use computational approaches and similar to solve these three simultaneous equations. But these three equations actually, especially since some of these terms are equal to 0, they shouldn't be too difficult to solve simultaneously. And we're going to do a sort of simultaneous equation method in this video to solve these. Let's start by doubling all of the terms in equation 3 here. And we'll end up with something that looks like this. We have 0 equals minus 8 V1 minus 10 V2 plus 58 V3. We've doubled all of those terms. And the reason I've done this, there's no sort of one correct way to go about this, but I'm looking at equation 1 here, which has an 8V1 term. And you'll notice that by doubling equation 3, I've now got a minus 8V1 term. And so what I can now do is I can add equation 1 and equation 3 together. And so on the left-hand side, minus 45 plus 0, we end up with minus 45 still. On the right-hand side, these V1 terms are going to cancel. I'm going to end up with 0 V1, as it were, because I've got 8V1 plus minus 8V1. We're going to end up with minus 10V2 and plus 55V3. So we now have an equation with no V1 term. Notice that equation 2 also has no V1 term. I'll just write that below here. So we have these two equations that don't have a V1 term, minus 0 V1. We can just say 0 V1. It doesn't really make a difference. So let's simplify by getting rid of these V1 terms altogether, actually. So now we have minus 45 equals minus 10V2 plus 55V3. And we have 8 equals 3V2 minus V3. So one thing we could do here is we could perform substitution. by rearranging equation 3 in terms of V3. So rather than 8 equals 3v2 minus v3, like we have here, we could say that v3 equals 3v2 minus 8. So let's now substitute this expression for v3 into this equation we had for 1 plus 3. We had minus 45 equals minus 10v2 plus 55v3. Well, rather than writing v3 there, we know now that v3 is equal to 3v2 minus 8. And so what we could do is make this substitution here. So now we've got minus 45 equals minus 10v2 plus 55, 3v2 minus 8. And if we expand that out, the brackets there, we have minus 45 equals minus 10v2 plus 165v2 minus 440. And we can rearrange to say that 395 equals 155v2, just by adding 440 to both sides, and these v2 terms together, we've got minus 10 and plus 165 v2. And that rearranges to say that v2 is equal to 395 divided by 155, or 79 over 31 in its Lord's terms. And again, we'll leave that as a rational number rather than round it, because we're going to use this value in just a second. Let's put this value into equation 2. So equation 2, we said, was 8 equals 3v2 minus v3. Well, now we know the value of v2. And so what we can say is we have 8 equals 3 times 79 over 31 minus v3. And again, we can rearrange and simplify a little bit. Let's expand that bracket. 3 times 79 over 31, we have 237 over 31. And that gives us v3 as being equal to 237 over 31 minus that 8. And we end up with minus 11 over 31. Now that we have the values for v1 and v2, we can substitute these into any of our original equations that had a v1 term. And we're looking to find v1. So we're going to avoid any of the equations that had 0 v1, because that doesn't really help us very much. Let's use our original equation 1. In its simplified form, it looks something like this. We had minus 45 equals 8v1 minus 0v2 minus 3v3. And we can get rid of that 0v2 term. We have minus 45 equals 8v1 minus 3. Well, rather than v3, I know now that v3 is equal to minus 11 over 31. So let's put that in there. We can multiply that out. That's going to give us double negative, first of all, becomes a positive. And 3 times 11 over 31 is 33 over 31. And we can rearrange to say that 8v1 is minus 45 minus 33 over 31. And that means that v1 is equal to minus 357 over 62. So we finish this exercise now to say that v1 is equal to minus 357 over 62 volts. v2 is 79 over 31 volts. And v3 is minus 11 over 31 volts. We could, of course, have found these using matrix methods, using the inverse matrix, or using methods such as Gaussian elimination. We could have used some kind of computational method to solve simultaneous equations, but it's useful to see that these systems of equations can still be solved using standard methods of simultaneous equations as well. But hopefully you've seen that it's very helpful to try and simplify those equations like we did at the start as much as possible to make that job easier.